All right, taking a look at example 4, we have a hemispherical tank that's filled with water and is to be emptied through its spout located 2 meters above the top of the tank. Determine the total work required to perform this task. So, first thing I'll say with hemispheres or spheres or anything having to do with a sphere, if you do not already have a coordinate system imposed upon you, which we don't, then you should center the origin at the center of the sphere. Or if you have a hemisphere, the center of the what would be the full sphere. So here is very important and useful for us to put our y-axis like that, or z-axis if you want to think of this in 3D, but really it's going to be sufficient for us to just consider a cross section. So we can do this in 2D. So there is the y-axis. What we're going to do here is we are going to consider a slice, an arbitrary slice. So I'll do this in red. So really, you are free to draw the actual circle, which is the cross section is a circular cross section, or you can just draw a line through it, and that's sort of what I do typically. Because if I were to not draw this with perspective and I were to just draw what a semicircle or what a lower hemisphere looks like, roughly speaking, it would just sort of be this, which is indistinguishable from a semicircle. So my point is the three-dimensional perspective and drawing here isn't really completely necessary. It's only there to help you visualize this. So what I'm going to do is I am going to draw just a little two-dimensional version of this. That's a little bit nicer to look at, I think. Okay, so there is my hemispherical tank. There's my y-axis. Here's my center. All right. So then I do know that my tank is my tank has that spout 2 meters above the top of the tank. I'm going to exaggerate this and say that this is well, this would be 2 if it's 2 meters above the top of the tank, because we are saying that our origin is right here in the center. So this technically is y equals 0. Now, the radius of the tank is 10, so this right here is, of course, 10. So what we're going to do is consider a slab of water at some y value, y. Now, what we want to know is, what's the area of this cross-sectional slab of water? So that is where it can be nice to think of this as actually being in 3D, because, you know, it actually is. Okay? So this is the area we are trying to find. So notice that this half really represents just the radius. So I am going to go ahead and draw these two like helper lines. This is a right angle. So of course, if this distance here is y, then this distance here is also y. So why don't we just call that y? And then because this goes from the center of the hemisphere to the surface of the hemisphere itself, that's a radius. That's the definition of a radius. So this is also 10. So this is 10. And then this radius that we want to know, this is of course going to change depending on what the value of y is. So this half here, I'm going to call this r. Because if I were to have drawn this cross section very low in the tank, then this radius r would change, because these cross-sectional circles get smaller towards the bottom, but as we go up in the tank, they get larger until we reach the middle, where it is the largest circle possible. So we need to have an expression for this area no matter where we slice our tank, whether we do it close to the bottom, right here where I did it, or at the very top. So thankfully this is a right triangle, so Pythagorean theorem applies. So we can use that to derive a relationship between y10 and r. Now why would we want to do that? Well, it's because we know the area of this cross-sectional circle is pi r squared, but we need to be integrating as we move upward because gravity acts in that upward direction, so that means the force is varying with y. So we need this in terms of y. So we go ahead and preliminarily write down what the area is with the understanding that we do actually have to take this a step further and get this into the variable of y. So using the Pythagorean theorem, we have r squared plus y squared equals 100. And since we are interpreting r as a distance, we can just choose the positive root of this. So this would become pi times the radius squared. Well, the radius squared is just 100 minus y squared. And of course, this is meters squared. So now the volume, of course, we would just multiply our previous result by the thickness, which is going to be, as before, dy. So that's dy cubic meters. And then we need the mass, which we obtain by multiplying the volume by the density, rho. So in some problems, they might not explicitly give you the density, so you can just write in rho to stand for the density, or whatever symbol you're going to use. So I should probably say someplace, let's just say it right here, let rho be the density of the fluid. And this would be measured in kilograms per cubic meter. That way, no matter who reads my work, they can see what rho means, and they can understand why this is here. Okay, so after that, we've got force, which of course is going to be found from taking the mass and multiplying by the acceleration due to gravity. Oops, and I forgot mass is kilograms, and force here would be newtons. Lastly, the work, which would be to take the force that we just have written down and multiply by something here to determine how far this slab must be lifted. So this slab must be lifted to this height of 2. Okay, so it's this distance we must travel. Well, we know this distance is y. So one thing I like to do is if you have these two horizontal guidelines and you want to know a certain distance, you just do top y value minus bottom y value. The y value at the bottom is just some arbitrary y value y. So the distance here must be top y value minus our arbitrary y value. Then we have 2 minus y, dy. And again, this entire sort of derivation here, is valid only for a slab. So for a single arbitrary, let's call it a slab of water or whatever is in this tank. So if we want the total work, this would have to be an integral of this last amount. So this would be g rho pi integral of 100 minus y squared times 2 minus y dy and we would integrate over some bounds. What bounds would they be? Well, we know at the very bottom of the tank, this would technically be a y value of y equals negative 10, since the radius is 10, and we're below the x-axis. So this is actually negative 10, and the water occupies this entire area. So from a y value of negative 10 at the bottom of the tank to a y value of 0 at the top of the tank. So the bounds for this integral would be negative 10 to 0. All right, that's it.